Okay, Assalamualaikum warahmatullahi wabarakatuh and good day class. So this is the video for the first chapter, first order ODEs, right? So this is the basic thing that you need to know in this chapter. So firstly, you need to know the basic definition and terminologies, and then the types of first order ODEs and the method of solution. So we have 5 methods here, and then we go to the application of the first order ODEs. Okay. So what is differential equation? So basically, differential equation is any equation which contains the derivative of either ordinary or partial derivative. So what is ordinary? So ordinary contains one or more dependent variables with respect to only one independent variable. Okay, so if you can see from this example, alright, you have dy over dx equals to 2x plus 3 d square y over dx square plus 3 dy over dx plus ay equals to 0. Okay, so if you can see from this example, you can see dy over dx, d square y over dx square, dy over dx here. Okay, so basically, the dependent variable is the variable on top here. Okay, and the independent variable will be the one at the denominator. So in this case, you have y as the dependent variable and x as the independent variable. Okay, so same goes with all with these two examples, right? For partial differential equation (PDEs), okay, it will involve one or more dependent variable and two or more independent variable. So, for example, um, let's say you have let's say you have dependent variable. Let's say you have y and z, okay, and independent variable maybe you can have u b w, for example. Okay, so let's say for this example you have del square u. Okay, why we use del instead of d? Okay, in ODE just now you have dy over dx, right? Okay, but here since it is differential equation PDE, we no longer use d, but instead we use del. Okay, so del will represent the partial differential equation. So if we are using del here, then you know it is partial. Okay, so in this case, u is the dependent variable and x and y is the independent variable. Okay, so same goes with this one. U is the dependent and x and t is the independent. Same, this also the same. Okay, let's say you have this function. So del w over del x plus del w over del t equals to 0. So here we can write as w with respect to x plus w with respect to t equals to 0. So from this equation, we know that this is dependent variable and these two are the independent variable. Okay, so same goes with this one. We have u as the dependent variable and x and y is the independent variable. Okay, now we go to the order of differential equation. So order of differential equation is determined by the highest derivative. So let's say you see this equation. Which one is the highest derivative? Dy dx, right? So dy dx, you see, it is just dy over dx. So the order is 1. Okay, so for the second equation, you have d square y over dx square plus 3 dy over dx. So this is the highest derivative, right? And the order is 2. Why 2? Because it depends on the highest derivative. Okay, so for the third example, you have d cube y over dx cube plus dy dx to the power of 4. Okay, so which one is the order of the d's? Is it 3 or 4? It is 3. Okay, why 3? Because we focus on the highest derivative. So this is the highest derivative. Okay, and the order is 3. Okay, now we go to the degree of differential equation. So the degree of differential equation is the exponent of the highest derivative. So to identify the degree, we need to focus on the highest derivative. So from the highest derivative, we see the power. Okay, exponent is the power, right? Okay, so we see the power. Okay, let's say the first equation, you have d square y over dx square plus 3 dy dx. Okay, here this is the highest derivative, right? But the power of the highest derivative is 1. So that's why the degree is 1. Okay. For the second equation, the highest derivative is 3, right? The highest derivative is 3. But the power is to the power of 1 here, right? So that's why it is 1, not 4. 4, it is not 4 because this is not the highest derivative. Okay. The highest derivative is 3. Okay, so for this equation, you have d square y over dx square and dy dx. So the highest derivative is this one and the power is 3. So the degree for this dE is 3. Okay, more examples. Maybe you can try and we'll discuss in class later. Okay, so linear differential equation. So how to identify whether the dE is linear or not? Okay, firstly, you need to see that the dependent variables and their derivative are of degree 1. Degree 1 meaning that one to the power of 1. The power of the dependent and the derivative is 1. And then you need to see the coefficient. What is coefficient? Okay, for example, let's say you have 3 dy over dx. So in this example, 3 is the coefficient. Okay. So each coefficient of the derivative depends only on the dependent variable. What does this sentence mean? It means that there is no product. No product. Product is the multiplication, right? Multiplication. So no product of um, the dependent variable, and its derivative. Okay, meaning that let's say you have y dy over dx. So this is not linear. Okay, let's say you have 3x squared, 3x dy over dx. Then this is linear. Okay, and one more thing, you need to know that there is no function of dependent variable. Okay, so we'll see after this the example. Okay, for this example, you have d square y over dx square plus 3 dy over dx plus 9y equals to 0. So this is linear. Why? Because you see the highest, the derivative is to the power of 1. Okay, and you can see the dependent variable also to the power of 1. Okay, it is linear. For the second example, you have d cube y over dx cube plus dy over dx to the power of 4 plus 6y equals to 3. Okay, so for this equation, it is nonlinear. Why nonlinear? Because okay, the derivative here is to the power of 1. Okay, um, the derivative here is to the power of 4. It is not okay. Okay, so this is not linear because of this 4. Okay, the next equation, you have x square d square y over dx square plus y dy over dx equals to x cube. This is not linear. Why? Okay, so if you see here, for the first term, we have x square and the derivative. It is okay. Okay, it is okay to have this because the coefficient here is in terms of the independent variable. But for this part, okay, the coefficient here is in terms of dependent variable. Okay, so this is not linear, right? Okay, the next one, dy over dx equals to sine y. So this is not linear because of this function of dependent variable. Okay, so let's look at the next example, x cube d cube y over dx cube minus x square d square y over dx square plus 3x dy dx plus 5y equals to ex. So this is linear or not? We will discuss in the class later. Okay, non-linear differential equation is other than linear differential equation. Okay, so boundary and initial and boundary values. So I think this one you already know. So initial condition will be given on specified given point. Boundary conditions will be given on some points. Okay, for example, you have y 0 equals to 1, meaning that when x equals to 0, y is equals to 1. When x equals to 0, y prime is equals to 2. So this is initial condition. Why? Because the x is at both at 0 at initial condition. But when it comes to boundary condition, you have when x equals to 1, y equals to 5. When x equals to 2, y equals to 2. So this is boundary condition because you have the x is from 1 to 2. Okay. So we have a problem with the initial value problem and boundary value problem. Later we'll do the examples on this, right? Okay, now we go to the first order ODEs. So we have 5 types. So in this video, I think I will discuss on the separable equation only, because I think if I discuss on the homogeneous equation, it will take a longer time. Okay. So maybe I'll do a separate video on homogeneous equation. So for separable equation, how to identify? It's easy, yeah? For separable equation, you can simply identify the separable equation if you can separate the two function. Okay? If you can separate function x and function y. So when you separate, you can move vy here to the left hand side and dx here to the right hand side. Become this equation, and then from here you can simply integrate both sides of equation. Okay, before we proceed, let's try to separate all of this equation, but for sure I won't do all. I just show you one or two questions, then the rest you can try. Okay, so let's do for question A. So you have dy over dx equals to secant square over 1 plus x square. Secant square y over 1 plus x square. Okay, so from here you can simply move this secant square y and this dx to the other side, right? So you have dy over secant square y equals to dx over 1 plus x square. So now you can simply integrate this equation. Okay. So for B, you have this equation. So from here, you have 3v over 1 minus 4v square dv equals to 1 over x dx. Okay, so try to do the rest. Okay, example 1, solve the initial value problem. Okay, but from here you know that to solve the initial value problem you can use the separable equation. Okay, so firstly you need to separate the function. So you will get 1 plus 2y square over y dy equals to cos x dx, right? So after that you need to integrate both sides. So you integrate so you can separate this 1 plus 1 over y plus 2 over y plus 2y dy equals to cos x dx. Okay, and then when you integrate you will get this one as ln y plus y square equals to cos x. You integrate, will get sin x plus c. You need plus c there. So use the initial condition when x equals to 0, y equals to 1 into this equation. X equals to 0, y equals to 1. So you substitute the values. So ln 1 plus 1 square is 1 equals to sin x plus c. Sin x, x is 0. Okay, so c is equals to 1. So from here you can rewrite your equation. So ln y plus y square equals to sin x plus 1. So this is your final equation. Okay, note that some DEs may not appear separable initially. Okay, from the equation you cannot see that it can be separated, but through appropriate substitution the DE can be separated. Okay. Example 2. Okay, show that the differential equation of this equation can be reduced to a separable equation by using substitution z equals to x plus y. Okay, then obtain the solution for the original DEs. So firstly, you need to differentiate both sides of the substitution with respect to x, meaning that you need to differentiate this equation. So you have z equals to x plus y. Why we need to substitute, why we need to differentiate with respect to x? Because of the original equation. Okay. So you differentiate with respect to x. So you have dz over dx equals to 1 plus dy over dx. Okay. So from here, you need to substitute into the dE. Where is the dE? This is the one. This is the dE. Okay. So from here, you can have dy over dx equals to dz over dx minus 1, right? So you substitute, you can get dz over dx dx minus 1 equals to x plus y square. So x plus y is equals to z square. So from this equation, you can use the separable equation to solve the DEs. Okay. So from here, okay, you can write as dz over dx equals to z square plus 1. So then you bring 1 over z square plus 1 dz equals to dx. Okay, so from there you can integrate the separable equation. So you can have 1 over z square plus 1 dz equals to dx. Okay, so you use the formula given, the list of formula that I uploaded in the e-learning. Okay, you can use that one. So you integrate 1 over z square plus 1, you will get inverse tangent z equals to integrate dx, you'll get x plus c. Do we have the boundary? No condition. Okay, so you have this one, but we need to convert back into the original differential equation. So now you have inverse tangent z is x plus y, right? Just now equals to x plus c. So rearrange, you can get x plus y equals to tangent x plus c. So y equals to tangent x plus c minus x. Okay. So I left you with the passive questions. We have 5 questions here. Okay, we have 5 questions. Then I want you to do the question, and I'll give you the answer for each of the question. Okay. For number 1, the answer is y minus 1y plus 1. For number 2, um, y equals to x minus 2, then x minus 1 square plus 2. Plus 2 because we have the condition there. And then number 3, general solution. So we have square root of y squared plus 1 equals to a over sin x. The next one is e to the power of negative 1 equals to minus e power x, x minus 1 minus c. And the last equation is y equals to tangent x plus inverse tangent 3 minus x minus 3. Okay, I wanted to try and we will discuss in the live class. Alright.